The second type of functional group that we're going to protect is alcohols. And there are a lot of ways that we could protect alcohols, and we're going to discuss specifically two ways. The first is as a trimethylsilyl ether, and this trimethylsilyl ether will be stable under basic conditions, and it will hydrolyze under acidic conditions, just like what we saw for the protections of ketones and aldehyde. In order to make our trimethylsilyl ether, we're going to take an alcohol like this one here. We're going to treat it with trimethylsilyl chloride in combination with triethylamine, and we're going to get our protected trimethylsilyl ether out of the reaction. So that this trimethylsilyl ether, this is sometimes referred to as TMS chloride, and you may use that abbreviation, where the TMS stands for the trimethylsilyl group. And we can also use that abbreviation in the final product, and I'll show you that in a moment. So what's going to happen in this reaction is that our oxygen is going to attack at the silicon. It's going to kick out that chloride in an SN2 reaction, and what we get is this. This is now in the presence of our triethylamine base, so that can grab that proton, and that will give us our final product, which we see here. I could also write the structure of this final product like this, where you see that TMS group abbreviation right next to the oxygen, and that's an acceptable abbreviation. Remember that whenever you have a protecting group, it's important that you know how to put that protecting group on, but also that you know how to get that protecting group back off. And when we do a hydrolysis of our trimethylsilyl protected alcohols, that's going to occur under acidic conditions, and that's going to give us back our alcohol. So that if I treat this compound with acid under the conditions of the reaction, I'm going to get the alcohol out of the reaction. I want you to work through this mechanism on your own. So I want you to take a look at the following examples. Pause the video and solve for the product in each of these reactions. In the first one, that alcohol proton is acidic and my Grignard is a strong base. And remember that one of the fastest reactions that will ever happen in your reaction flask is that acid-base reaction, where your strong base rips the acidic proton off. During the course of this reaction, at the end of step 1, what we're going to have is this. So that at the end of step 1, what we're going to have is that alkoxide ion and a molecule of ethane that came from our Grignard reagent. And then in step 2, when we do our acid workup, we'll get our original starting material back out of the reaction, plus that quenched Grignard reagent, so a molecule of ethane. So there's no productive reaction that has happened. If we need that productive reaction to happen, we have to put a protecting group into our structure. So in the second one, we're going to add that protecting group. So here we have that same molecule, and I'm going to treat it with TMS chloride and triethylamine, followed by my Grignard reagent and an acid workup. When we predict the product out of that reaction, after step 1, what we're going to have is our protected alcohol. That means that when we treat this protected alcohol with ethyl magnesium bromide, followed by our acid workup, the alcohol functional group remains hidden, so that the final product we're going to get out of this reaction is this one. Notice that my workup step was just an H3O plus workup. And remember, we said that those are conditions that will quench my Grignard reaction, and also remove my protecting group. So here we see that protected alcohol revealed again. For the next one, I have the same series of reactions as I did in the previous question, but instead, step 3 here is going to be my dilute acid workup, which will leave my protecting group intact, so that at the end of this sequence of reactions, the product that I get is this one. Where my alcohol remains protected, and I could carry it forward through an additional reaction if I wanted. So that this step is going to keep my protecting group intact. We're also going to look at a second way that we can protect our alcohols, and that is as a THP ether, or a tetrahydropyran ether. Just like our other protecting groups, this protecting group is going to be stable under basic conditions, and it will hydrolyze under acidic conditions. So the reaction to put this protecting group in place looks like this. I'm going to take my alcohol, I'm going to treat it with dihydropyran in the presence of acid, and I'm going to make my protecting group. So what I've done is I've replaced this hydrogen on my alcohol with this giant THP group. What functional group is present right there at that carbon? It's an acetal. So I've used my alcohol in combination with my dihydropyran molecule to make an acetal functional group. We know that acetals are stable under basic conditions, and we know that they hydrolyze under acidic conditions. Make sure you can go through the mechanism for this reaction on your own. When I need to take my tetrahydropyran group off, I'm going to treat my compound with acid. So again, I'm going to remove this entire group, and I'm going to replace it with that proton. So I'm going to take my acetal functional group, and I'm going to convert it to an alcohol. Make sure you can work through this mechanism on your own. So if you look at an example like this one, pause the video and predict the product of this reaction. During this series of reactions, this is the final product that you get. In step 1, we're going to protect our alcohol using the dihydropyran group, and this is the product that we get. In step 2, we're going to do our Grignard reaction, which will react selectively with the ketone, leave my acetal functional group for my protected alcohol intact, and give me this product. Step 3, then, with my acid workup, I've not specified that it is a dilute workup, so in step 3, the product that I will make out of this reaction is my protonated alcohol as a result of the Grignard reaction, but also the removal of that THP group. So the final product of my reaction is this compound, along with the regeneration of my dihydropyran ring structure. So if I need to protect a carboxylic acid, I can protect a carboxylic acid as an ester. So I might use diazomethane as a very mild reagent in order to make that methyl ester. So that in step 1, I'm going to convert my carboxylic acid to the methyl ester. And then in step 2, when I use PBr3, I'll get a selective reaction of the alcohol. I won't have any risk of converting the carboxylic acid to an acid bromide. So in step 2 then, I'll make this product. When it comes to the reagents that I might use in this case in order to convert this carboxylic acid to an ester, diazomethane is a good choice. Potassium carbonate in combination with iodomethane would also be a good choice. You should think about why your Fischer esterification conditions might not be the best choice in this specific reaction. The last group we're going to discuss is amines. If we need to protect an amine, we can protect an amine as an amide. Consider the following reaction. What would happen if we treated aniline with nitric acid and sulfuric acid? Think about this reaction. What would the product be? It's not the product that you probably would have predicted way back in our discussion of electrophilic aromatic substitution. Is this the product you predicted? This is a very acidic reaction, so that if we have an amine, which we know to be a good base under the conditions of this reaction, in the presence of nitric and sulfuric acid, your aniline compound will be completely protonated. So that once we have this in our reaction, this ammonium ion is now a meta-director. Whereas the amine that we would have been expecting, this is an ortho-para-director. So that under the conditions of the reaction, this is the product we're going to get, not the ortho or para product that we might have originally predicted. In order to be able to get that ortho or para product, we need to protect that amine as an amide. So instead, we could take aniline, we could treat it with an acid chloride in the presence of triethylamine, and we could make an amide. Our amides are not basic like our amines. So when we treat this amide under acidic conditions with the conditions for the nitration reaction, we'll get the nitration product. In this case, I'm showing the para product. I'll also get the ortho product. From there, if I take this compound and I treat it with KOH, water, and heat, those are conditions that will hydrolyze my amide, give me back that amine, and so this is the product that I got. So that if I wanted to make that para-nitroaniline compound, this would be the synthetic pathway that I would have to follow. The direct nitration of aniline would not lead me to that para product.